Okay, good morning. Hopefully you were not scared. So it's time to get started with the lecture for this morning. So please turn off your computers or the screen. Let me turn off the lights here. That work? Okay, so before we get started, on Tuesday, we're having a visitor coming to our lecture. So I just want you to be aware if you see a faculty sitting back there, don't get scared. It's just a faculty who want to watch the next lecture. The other thing is we are 2 weeks before the exam, actually. So the exam is going to be in 2 weeks. So I want you to be aware of that. Get prepared. Get ready for the first exam. The best way to study for the exam is to go through the lectures, practice the problems we've been discussing, and also work with the homework. You're going to have the second homework. Today I'm going to post the second homework. That homework is basically addressing the graph method for solving linear programs and also the formulation. So I'm going to give you some practice. The best way to prepare for the exam is to work on those problems on your own. If I don't mind if you want to get together, discuss them, understand what other colleagues are doing, but you have to submit your own homework. Okay? So we are meeting 2 students today, and hopefully they'll be here. This is a very important lecture, again. This is the basic for this topic, actually for the course. If you don't understand how to formulate the problems, then knowing how to solve them is kind of not how you're halfway there. But the most important part is now how to model these problems so you can actually get to model real problems in your career. Again, as I mentioned last week, you can solve these problems using the computer. So solving them is not the hardest part. The hardest part is basically know how to model the problems. So going back to the same slides, the objective for this lecture, so I want you to be able to formulate linear programs. And we are going through these examples. Last time we only covered the diet problem. Today we're going to look at more real type of problems that you're going to be seeing in your profession, such as production planning, scheduling, specifically for your resources, and also if you have to work with some type of equipment such as the bus scheduling, there's a problem there. Also for government type of problems in which you're planning for urban development, there's also a very good application. You get to a management position, how to select the next project for your area. There's a problem here, project selection. And finally, if you go to work for an oil industry and you're asked to find the best mix of your product to get the output that you need for a certain period of time, there's a problem here that addresses that problem. Okay, so these are very typical problems that you can find in the industry right now. So if you get to formulate this type of problem, that will be useful in the future. So I went through these guidelines again. I can teach you the rules, but it's only through practice that you'll be getting used to formulate problems in operational research. So get practice, go through the examples, and work with the homework. We went through these. These are basically the steps. So identify the decision variables, formulate your objective function, identify the constraints, identify the decision variables and how are they related to your constraints, make a dimensional analysis to make sure that the objective and each constraints are consistent. And also remember that this is an iterative process. So once you formulate your model, you might need to go back and revise that model until you get to the good model for your problem. So we discussed the type problem. We went through the steps of how to identify the question that we need to answer and so on. So we can decide what decision variables we need, how to formulate that objective function, and how to formulate the constraints. So that was our formulation, our linear program formulation for the first problem, which is the diet problem. Now, let's get to discuss this problem about production planning and inventory control. So I want to make a quick question, maybe, or go by one. Just to get an idea, where do you see yourself working after you graduate? Do you have any specific industry on your mind? Kids are here. Do you have any idea where you want to go work after you graduate?
I like to work in like the oil and gas.
Okay, very good. Do you? Okay, very good. Same?
I'm going to do manufacturing.
Okay. Okay. Simple project planning, everything. Good. Okay, very good. So I think the problem issues for the class today will be kind of directed to those interests. So just let me know if you have questions. Raise your hand. If you think that a good big problem, how would affect the actual formulation. So let's start with this production planning. So here we have a preparation for winter season. A clothing company is manufacturing these type of jackets or parka boots, overcoats, insulated pants, and gloves. All products are manufactured in 4 different departments. So you have 4 departments in terms of the production, cutting, insulating, sewing, and packaging. The company has received orders for this product, so you already know the demand for your product beforehand. You know how many you need to produce in the following weeks. So the contract stipulates a penalty for undelivered items. So you already have the order, you need to satisfy that demand. If you don't satisfy that demand, you're going to be penalized. So the table here provides you with the details in terms of how much time do you require to produce each type of item. So you know you have to go through these 4 stations: cutting, insulating, sewing, and packaging. Here you have, for example, for the first product, parka, you need 30% of an hour to produce 1 item. 20%, 25%, so this is 15 minutes for this process, 45% for this process, and 50% of this for this process. So each one of these items have a requirement in terms of the capacity, in terms of the time required to perform each one of these tasks. You also have a capacity limitation in terms of the hours that you have available to perform these tasks. So that capacity limitation is in terms of your resources. So in terms of capacity, we are naming the capacity in terms of hours. So we have 1,000 hours for each one of the departments. So only 1,000 hours to produce, actually to perform each one of those tasks, 1,000 hours, and you need to use that capacity to produce the demand that was requested. And you know the time that each product will require. Now, you also have the demand to satisfy for each product, and you obtain a profit for each unit of $30, for example, for parka, $30. But you also have a penalty if you're not able to deliver the products. Okay? So for each unit, you have a penalty, and also you have a profit. The problem clear? So what will be the question to be answered? You have capacity limitation. You need to produce certain type of products using your capacity. And you have some profit and penalties for not basically producing the demand that is requested. So what is the question? Correct. You want to know how many units of each type you need to produce. So we're going to use just one index to identify the product in one variable that is going to tell us how many units of each type are you going to be producing. Okay? So very good. We can state those variables in terms of the product. So X1 will be representing the jacket, parka jacket. X2 will represent the goose jacket. X3 will represent the pair of pants. Excuse me. And X4 will represent the number of pair of gloves. Okay. So we have our decision variables. We need to identify, find out how many of each type are we going to be producing based on the capacity limitations and based on the requirements in terms of time that each unit will require for each station. Can I move to the next slide? Okay, so what will be the next thing to do? You know your decision variable. Decision variables in this case. What is the next step? It's to formulate your objective function. So in this case, I'm presenting the table one more time because we're going to be using it. So in this case, you're producing some items, so you want to maximize your net profit. Do you know how much profit you're going to make for each unit? Do you have the cost for this problem? Right, you have the penalty cost if you're not able to produce the number of units that are requested. So your profit will be defined in terms of the total profit minus the total penalty. But what happens? You can basically list or define your total profit based on the units that you're producing times the profit that you're going to make for each one. So for the first unit, which is the party jacket, $30 times the units that you will produce, $40 times the units that you will produce, and so on. Now you need to find a way to address the issue about the penalties. And one way to do that is by using a new variable that will represent those units that you're not able to produce. I'm going to call that variable S. So the total penalty requires the use of a new variable, S, representing the shortage in demand for product J. So you'll see how this variable is used in the constraints so we can formulate the problem properly. So I'm going to define that penalty, and the total penalty is defined for each item. So I have an S1 for the parka jacket. I have an X2 for the goose jackets, and so on. So anyone can tell me what will be the actual objective function? How can you use those two to perform or to create a objective function? You have total profit, you have total penalty. Yes.
X and S, or you put S and
Say that again?
Can you use both X and S?
Yes, you can again. For example, I'm using X here. You can use different letters to identify those X. This is just the easiest way to do it. You can keep the same letter and use some indices to identify the specifics. In this case, you can also, instead of use S, you can use X and say X6, X7, X10, and so on. And you know that 6, 7, 8, 9 will represent the penalties. But in this case, just to make it clear that there's a difference between two, we're using two different variables. Okay? So to formulate the objective function, you just have to sum the profit and subtract the actual penalties. Makes sense, right? So you're going to make some profit, but if you're not able to satisfy the demand, then you incur on that penalty. And we are trying to maximize our profit. That's very important. You are trying to maximize your profit by selling those units that will generate a profit when you take into account the penalties. Any questions so far? Very good. So now we need to define our constraints, and I already list them here. So let me walk you through the constraints. We have 4 constraints in terms of the capacity for each station, right? So we have a cutting station that has a capacity of 1,000. That will be our first constraint. We know that the units that we produce for this item, and the units for this item, units for this item, and the units for this item, the summation of the units times the time that requires to create or to perform this specific task, this needs to be less than or equal to 1,000 hours. So our first constraint will basically say 0.3 of an hour times the number of units for the cutting station, plus same for goose, hands, and glove, needs to be less than or equal to 1,000. So you will not exceed the number of hours that you have available for that station. And the same thing happens for the insulating, sewing, and packaging. So your first 4 constraints are addressing this capacity limitation for production. Now, we need also to add some constraints that use the demand for our problem. So the demand for the first item is 800. So you can say, okay, X1 needs to be equal to 800. But what happens? If you are not able to produce that many items, that constraint is going to be violated. So the only way that you can satisfy a equal constraint, like this one, is by adding another variable that will take the values needed to make this equal to 800. So we have 3 constraints, actually 4 constraints for the demand. This is the first one. This is the second one, third one, and fourth one. Okay, so if we say X1 equals 800, then we are forcing the problem to make X1 equals to 100. But if you're not able to produce that many units with the capacity that you have available, that problem will become infeasible. You will not be able to solve or find a solution. Now, if you have the second variable, let's say that you are only able to produce 750 equals X1, then 750 plus S1 will be 800. So X1 will be equal to 50, and that will be the units that are going to be penalized using this cost. Okay, so by putting them together, these will balance in such a way that you can use this equal sign for your constraint. Because you know that you need to satisfy that demand. If you don't satisfy that demand, then you're going to have to pay the cost for your unit that you're not able to deliver. Okay, so you have 4 constraints for the capacity, and you also have constraints for the demand. And the problem, what it's going to do is it's going to assign X1, X2, X3, X4, X5 and x1, x2, x3, and x4, such that you can maximize your profit. Any questions? Okay, so this problem is what we call a single period production problem. You are making the decision now for the next period, just one period. Okay, but in reality, let me go to the actual formulation. Here you have the LP formulation for the single period production problem. Objective function, constraints, and bounds. But in reality, you are faced with problems that are multi-period. And that's our next example. Yes.
Think about it.
Yes.
Would it be smarter to solve that, all the S's in terms of X, and put that back into Z? So you have simplify the Z.
Solve this in terms of X.
Yeah, so S1 would be 800 minus X1.
And then put that over there. Yeah, that can be done. So you will have your objective function based on only one value. Yeah, that's something that can be done. It will simplify, I guess, it will simplify your objective function, but you still have to use your X for your constraints. Yeah, that's something that can be done. Maybe. Any other question? Good. So now we're going to look at the multi-period production problem. So in this case, we have a manufacturing company that has a contract to deliver 100, 250, 190, 140, and so on, windows over the next 6 months. So for the first month, you're going to need 100. For the second month, you're going to need 250, and so on. And you have the production cost per window that varies by period, and it's estimated to be 50, 45, 55, 48, and so on for the next 6 months. So you have a variability in terms of the cost for production, and you also have the variability in terms of the unit that you're going to need per month. So first month you're going to need a certain amount, second month you're going to need a certain amount, and also your costs are going to be changing per month. So to take advantage of those fluctuations in manufacturing, what we usually do is to produce more windows than needed in a given month, and you can put some of them in your inventory, so when you need it, you can sell them. Okay? And that's the type of thing that we're going to do in this problem. So we're going to produce more windows than needed in a given month and hold the extra units for delivery in later months. So you can take advantage of the fluctuations in terms of the cost. So this will incur in the storage cost at the rate of $8 per window. So if you put that into your inventory, you also have to cover the cost for your warehouse or your storage, and that will be $8 per window per month, as of the end of the inventory. So we're going to use this information to develop our LP, our linear program, to determine the optimal production schedule for the next 6 months. The problem here, okay, so we have some demand that is based on the multi-period, 6 months, and we have some costs that are changing according to the month. And we have also a cost for storage. If you decide to produce more units in 1 month and you don't use them, you have to incur in a storage cost for those units that were not used in that month. So what would be the question to be answered? Question to be answered. This is a production problem. So again, we need to know how many units we need to produce, right? It's a production problem. We need to find out how many are we producing. Is there any other question that we need to answer? Call the inventory part. We are not purchasing, we are selling. Yeah. And how many? Correct. So we are going to produce some units. Some of them are going to be in the storage. So how many units are we going to left in the inventory per month? Those are the two main questions. So we're going to use an index for the month of the year, and we're going to have two decision variables: the number of units to be produced in a month, and the inventory units left at the end of the month. So you can see how the questions to be answered are related to the actual decision variables. Because at the end, what you want to know is the answer for those questions, right? So if you are able to formulate those questions, then you can easily define your decision value. Okay, so we have two decision variables, one for the units produced per month, and one for the inventory left at the end of the month. Okay, move to the next slide. Okay. So the variables of the problem include the monthly production amount and the end of the month inventory, right? So those are our decision variables. And now we're going to use this diagram to explain you how these variables are related. So the relationship between these variables and monthly demand over the 6-month horizon is represented in this figure. So if you're starting your production from day one, how many units you will have on inventory at the beginning of your production cycle? 0, right? So there's no inventory. You're going to start from scratch, from 0. So when you start at time 0, you have no inventory. So your inventory is 0. So you're going to have to produce X1 units to satisfy this first demand, 800. And how many of you took engineering economic analysis already? Remember the cash flow diagram? That's basically what we're trying to do here. It's a certain type of cash flow diagram. So you put your requirements here for time period, and then you're trying to satisfy those accordingly. So you know that you need to produce some items to satisfy this demand. But you can also produce additional items that you can take to the next period as an inventory. So if your time period 1 you need only 100, you can produce 100 and your inventory for the next period is 0. But if you produce 200, then you're going to be using only 100 and you will carry 100 units for the next period. So that's where this arrow and this arrow intersect. So you're going to have some inventory and some additional production for that month. And the process is repeated. So here you have the inventory from the previous period plus the production for that period. That should be enough to satisfy this demand. And if it is more than that, then you can take that additional unit to the next period as your inventory number 2. Okay, until you get to the last one, so you can produce as many units as you need for satisfying this demand. And if that is your last period, then you will not require to carry any additional inventory for the next period. So using this format, we can move to the next steps of the model. So the objective function, again, you have, go back here, you have the cost, right? You don't have a profit defined for your units. The only thing you have in the problem defined is the cost for producing those items, and the cost for storage. There's no profit defined in this problem. So that will affect how do you define your objective function. So if the only thing that is involved is the cost, then you're going to try to minimize or maximize your cost. Minimize the cost. Okay? So you're going to minimize the total cost of production and then of inventory for that production cycle. So your total production cost is the cost for producing those items on every month. And also, you have a cost for the inventory. So if you carry these many units, it doesn't change. So the cost is going to be the same. And you basically multiply that cost times the inventory that you need for each month. So your objective function again is stated in terms of minimizing your production cost plus your inventory cost. Make sense? Okay, so we are trying to minimize our cost, and the costs have two areas, the production and the inventory. Can I move to the next one? Okay. So now let's look at the constraints. So we're going to be using this diagram one more time to define our constraints. So the constraint of the problem can be determined directly from the figure. So essentially you need to satisfy a demand, which are those arrows here, per month. So you're going to have the constraint per month. And for the first period in which you have to satisfy this demand, the only thing that you're going to have available is the number of units that you will produce. And you will have to subtract the number of units that you will take as an inventory for the next time period. So you can write this on several ways, but at the end, we'd like to have our decision variables to the left and our parameter to the right. So the easiest way for me to define this constraint will be, so 100 minus the inventory will be equal to the amount that I need to produce. Okay, so I know that I have to produce 100. If I decide to do some inventory, then I need to produce these many units. It will be plus. Yes, it will be plus. Sorry. If I want to take 100 units for the next month, and I know that I have to produce 100, then the number of units that I'm going to be producing is 200. And using this, I can move my parameter to the right-hand side and my decision variable to the left and come up with the constraint. Same thing for the second time period. So we have 200 here. We are going to be taking the inventory from the first time period plus the production. So you're going to add those two and subtract the inventory that you're going to take to the next time period. And that should be equal to this 250. So I need to know if that makes sense. Is that clear? So you have to take each case independently. So in this case, you have no inventory, so that's why you only have two decision variables. But here you already have this coming from the first period, your production, and also the inventory that you're carrying to the next time period. So that's why we have three decision variables here. Okay? And you repeat the process until you get to the last one. This one, you only have the inventory plus the production. You don't need to take anything to the next period because there's no demand here. So you only have I5 plus X6 equals that demand. Okay? So that basically gives you the formulation for the problem. You have your objective function, your decision variables, and your bounds. Any questions at this point? Okay? Those two problems, again, are production planning problems. Now, we're going to move to the next application, which is also very used very frequently. A lot, especially if you are in a managerial position or supervising position. You need to plan about how to use your human resources effectively. And if you need to add another person for your production, you'll be using this. You need to find out where, how many. Okay, so let's look at several applications. So this is the bus scheduling problem. And here we have a city that is studying the feasibility of introducing a mass transit bus system to reduce the in-city driving. The city seeks to the minimum number of buses that can handle the transportation needs, and the required number of buses will be approximated by a constant value over the successive 4-hour interval. So you have the 24-hour period for a day, and for each 4-hour time period, you have the number of buses that you require. So for the first 4 hours, from midnight to 4 a.m., you only require 4. Then from 4 to 8, you require 8, and so on. So that's basically the capacity that you will need to satisfy the demand during those 4-hour time periods. Now, to carry out the required daily maintenance, each bus can operate 8 hours, 8 hours successive hours a day only. Which means that if the bus starts his shift at this point, he can only operate until 8, and then it has to be taken to maintenance. Okay, so you have to take into account not only the 4 hours, but the 8-hour time period to plan for your capacity. Okay, so we're going to use LP to determine the optimal number of buses in operation by taking those constraints into account. So again, what is the question to be answered? I just said, just answer the question. And actually, if you go back to the slide, yeah. Right. Is it how many buses you will need per shift? Okay, so I'm going to use an index for the shift number. And then my decision variables are the number of buses needed in shift time. Okay, so I want to know how many buses I will need for each time period. Okay, so the variables of the models are the number of buses needed for each shift. So if we refer back to the graph for the capacity demand of the number of buses, you'll see that you can define your variables in terms of 8-hour shift. So X1 will be these 8-hour shift from midnight to 8. And then you can have another shift starting at 4, from 4 to 12. And then another shift starting at 8 until 4. Another one starting at noon until 8. From 4 to midnight, and one from 8 to 4 a.m. So you can have 6 shifts in your schedule. You can define this shift as you want. Again, the only limitation is that you need to satisfy the 8-hour constraint. So each shift should be of 8 hours. So if you want to start a shift here 4 to noon, that's also okay. You don't have to define it as this, unless it's already specified. At the end, you should be able to get the same solution. Okay, so for now, I'm going to define them like this. And I'm going to use those decision variables to establish the number of buses starting at 12. I know that the buses that start here will be available until 8. And buses at X2 will be available from 4 to 8. And so on. Okay, so you can have six shifts for your schedule. Okay? Any questions? So the definition of these variables is kind of difficult, but once you see it, you can apply this to other problems. So just be aware that you need 8-hour shift and define your variables in terms of your time period. Okay, so we have those variables. Now, the objective function will be to minimize the number of buses that you have in operation. Okay, so you want to minimize your x1, x2, x3 until x6, which are the numbers that you're going to have, number of buses that you're going to have working during each time period. Excuse me. Okay, so from there, the only thing that we need to do is to establish our constraints. So because of the overlapping of the shift, the number of buses for the successive 4-hour periods can be computed as this table. So you know that from 12 to 4 a.m., which is this time period, you're going to have the buses from the first shift. And you remember shift 1 goes from here to 8, right? So the buses for the first shift are going to be available during this 4-hour time period. There's another shift that is going to be available. Which one is it? We go back to the figure. Shift number 6, which starts at 8, continues until 4 a.m. So that shift is also available during this time period. So for that reason, we can define the number of buses in operation in this time period as x1, x6. Okay, so let me go on here. So you have x1 there, and then you have x6 starting here and continuing here. So those are the variables that will be serving customers during that time period. So you can define the number of buses as x1 plus x6. Same thing applies for this one. So for that one, you know that x1 is going to be here because the shift ends at 8, so x1. And x2 will be from 4 to 12. So x2 will also be part of the second time period. And following the same analysis, you can state the number or the variables that are going to be used for each time period. And then once you have identified that, you have the constraints that you need to satisfy. So for the first 4 hours, you need at least 4 buses. For the second time period, from 4 to 8, you need 8 buses. For the third one, you need 10 buses. For the fourth one, you need 7 buses, and so on. So you have a lower bound for the number of buses that you will need. And those are your constraints for each time period. Okay? So you need to identify the question that you need to answer, how many buses. Then you want to minimize the number of buses that are operating in your system. So you can make a decision in terms of how many buses you will need to buy. And finally, you will identify how many buses will be operating for each time period. Any questions? Okay, so this is a scheduling problem, and I have a second problem that is kind of similar. This one addresses the problem of full-time employees on different days of the week. So it is also a scheduling problem, but looking at the employee's schedule, basically. So post office, and actually we had a project addressing this problem last year, I believe, in our senior design. So they were looking at the capacities for a post office office. I think it was here in San Marcos. I don't remember. But this type of analysis was used for a real problem. So you have some number of employees required per day, basically, and the union rules state that each full-time employee must work 5 consecutive days and then have 2 days off. I know most of the post offices are not open on Sunday, but I think for making the problem easier, I'm just adding that extra day. Okay, so post office wants to meet its daily requirement using only the full-time employees. So we need to formulate our problem so each employee works for 5 days and take 2 days off. And also we can satisfy the demand, well, the capacity demand. So what is the question to be answered? Anyone? Exactly. Very good. So how many employees do you need to work each day? Very good. So I'm going to use an index for the day of the week. And my decision variables would be the number of employees beginning to work on a day. Okay? And I know that if I say 3 employees will start on Monday, they will be working until Friday. And then they will take Saturday and Sunday free. If I say that they start working on Tuesday, same thing happened. They will work until Saturday. They will have Sunday and Monday free. So that's my decision variable. The objective function is to minimize the total number of employees. So the number of full-time employees will be equal to the number of employees who start work on Monday, Tuesday, and so on until Sunday. So you're going to be minimizing those number for each day. So your number of employees per day. The summation of those is what you want to minimize. Again, if you have less workers, you'll have to spend less money. So that's what we're trying to find. That's your objective function. Need more time to write that. Okay. So what will be the next thing to do? Formulate your constraints. So the post office must ensure that enough employees are working every day. So you need to answer who's working every day. Everybody except the employees who need to work on Tuesday or Wednesday will be working on Monday. So those that started working on Tuesday and Wednesday will not be available on Monday because they're going to be free that day. They get respectively Sunday and Monday, and Monday and Tuesday off. So to ensure that at least 17 employees are working on Monday, we require that the constraint will be X1, X4, X5, X6, and X7 being greater or equal to 70. Because we know that the only employees that are going to be working on Monday are the ones that start on Monday and the ones that start on Thursday, Friday, Saturday, and Sunday. The ones who start working on Tuesday are going to be on their free day on Monday, and the ones who start working on Wednesday will be also free on Monday. So the only way that we can satisfy this constraint is by assigning employees to come Monday, assigning employees to come on Thursday, and until Sunday. Does that make sense? See what we're trying to do? We want to assign some employees to start working on Monday to satisfy the demand for Monday. We cannot assign anyone from Tuesdays or Wednesday because if they work 5 days in a row, they're going to be free on Monday. Those are Tuesdays and Wednesdays. But we can assign people on Thursday, Friday, Saturday, and Sunday to satisfy that demand for Monday. And you repeat the process for each day. So for Tuesday, instead of Tuesday, now you have people who start working on Wednesday and Thursday will not be available on Tuesday. Same thing for Wednesday. People starting on Thursday and Fridays will not be available on Wednesday, and so on. So if you go to Sunday, people starting on Monday and Tuesday will not be available on Sunday. And using those variables, then you want to satisfy these lower bounds. And so that is your formulation. Okay, so before we go to this planning, I have a lab for you that is essentially a big scheduling problem. So just want you to try to formulate a problem of this type. You can work in teams of 2, so you can work together. I guess you'll be working together. And then you can work together. And try to find out if you can formulate based on our discussion that problem. There are several ways to formulate a problem or this type of problem. Again, you can use different type of variables or multiple variables or the same variable with the index. So if you don't have the same solution as your student fellow, does not necessarily mean that you have a wrong model. And problem is a little bit challenging because you don't have the constraint of having the person working on the same 2 time periods in a row. You can also have them work one time period, get the other free, and work on the other. So that adds some complexity to the problem. And since you are here, you'll get 5 points for trying. If you get it right, then you get an extra point for the exam. Will it help if I told you that you can use this decision variable xij, saying that these are the workers working shifts I and j. and you have 4 sheets. Could be first shift, second shift, first shift, third shift, first shift, fourth shift. What would that be? So if you have x1, 2 equals 3. Say that again?
I did everything. We didn't.
Need sheet? Yes. Here you go. So if you say x1, 2 equals 3, that means that 3 employees are working the first shift and the second shift. Okay, I'll give you 2 more minutes so we can discuss the problem.
X I J.
Xij could be consecutive or non-consecutive, depending on how you define numbers. So if it is consecutive, you have 1 and 2, 2 and 3, 3 and 4, 4 and 1. Those are consecutive. Then you have 1 and 3 that are non-consecutive. So you can define those combinations and use them for your one. So you know that if they work 2 shifts in a consecutive, then you pay them 12 hours. So 2 consecutive shifts would be 12 hours. So 12 times 12 is 144. That could be part of your objective function. You can take that cost and multiply those x that represent the shifts that are in a row. And then for those that are working separate shift, you can list those x that represent the separate shift and multiply those shifts, those x times the cost will be 12 times 80. And you want to minimize that cost. That's okay. I mean, you still get the 5 points for that for trying. I just want you to get into the mental process of formulation. Yes. Yes. These are coming from the book, actually. The ones that I'm explaining, most of them are coming from the books. Yes, chapter 2 is listed at the first part. Yeah. So for the homework that I'm going to be posting today, I would recommend you to read. I'm going to put it in the homework. Read chapter 2, formulation. That would give you an idea. But most of the problems that we are I'll discuss are coming from the book, from the textbook. So you will have an idea of what type of problems you'll see. So let's discuss this. You pass your sheet. You put your name on it. Okay. So this is the decision variable again. Ij equals the workers working on shift I in J, and we have 4 shifts. So we can list the different combinations for shift in a row. So you can have x1, 2, x2, 3, x3, 4, and x1, 4. Those are the shifts that are in a row. The last one is 4-1, but I'm just keeping the same format. So this could be 4-1. Okay, and then those that are not in a row are those x1, 3. Then you can also have x2, 4. I believe those are the other ones. Is it that one? Yeah. Same one as 1, 3, 1. It's the same. Yeah. So, so now we have this information, and using this we can formulate our objective function. So you know that you're gonna pay 8 hours, 12 hours, I'm sorry, for each employee, depending on their particular shifts. So for those that have shifts in a row, you'll pay $144 because they're working 12 hours at 12 hours, and those are x12 plus x23 plus x34 plus x41. Does that make sense? Make sense? Plus 18 times 12 is 216, and those are x13 plus x24. So what you're trying to do is to minimize that cost, right? So our objective function is minimizing that. Okay, so now we have our objective function. Let me see if I can move to another slide, maybe. Okay, so for the constraints, we're going to have 1 constraint per shift, and we have 4 shifts. So for the first shift, we only have the employee starting at 1, 2, plus the employee starting at 1, 3, plus the employee starting 1, 4, and those should be greater than or equal to 50. Because that's the requirement for the first shift. So this is shift 1. Then for the second shift, we have x12 plus x23 plus x24, and that has to be greater than or equal to 5. and this is shift 2. Then for 3, same process, x13 plus x23 plus x34 has to be greater or equal to 12. And for the last shift is x14 plus x24 plus x34. This has to be greater or equal to 6. And then you have all your xij's greater or equal to 0. So I'm going to post this solution on tracks. I've been posting all the lab solutions, so if you want to refer back to the labs, they are posted. And I'm going to do the same thing with this one. So before we go, I'm going to just discuss one more problem. This is the urban development planning problem. And in this problem, what we are looking at is at the city budget. So the city is facing a very severe budget shortage. And the city council votes to improve the tax base by condemning a inner city housing area and replacing it with the modern development. So the project involves 2 phases: demolishing substandard houses to provide land for new development and building the new development. Okay, so we're going to demolish some properties and we're going to build some new ones to try to work with this budget. So this is a summary of the situation. We have 300 substandard houses that can be demolished. Each house occupies this space, and the cost of demolishing a house of this type is $2,000. Then we have lot sizes required for single, double, triple, and quadruple family homes, and those are listed here. These are the requirements in terms of space. And we also need to consider the street open space and utility easements account for 50% of the available space. In the new development, the triple and quadruple units account for at least 25% of the total. Single units must be at least 20%, and all double units at least 10%. And here we have the tax divide per unit for single, double, triple, and quadruple: 1,000, 1,900, 2,700, and 3,400 respectively. And we also have the construction cost per unit for single, double, triple, and quadruple. And we also have a limitation in financing, which is 15 million. So the question is, how many units should we demolish and how many units of each type should we build based on that information? And that's a lot of information. So, use this information, but the first thing you have to do is just try to answer the question. And I just told you, you need to find out how many units of each type are you going to build and how many houses are you going to demolish. So, that's your objective or your question to be answered. You also want to maximize the tax collection by trying to build as many houses as you can and collecting those taxes. Your indexes is the type of home, and your decision variable is the number of units of each type of home. Okay, and the ones that you're going to demolish are also part of these variables. So you have x1 equals single, x2 equals doubles, and so on. And then you can have x5 for those that are going to be demolished. Let me move to the next slide. Okay, so the variables again, number of units to be constructed. So as I mentioned, depending on the type of house, you can use an index to define the type of house, and also I'm using x5 for the number of all homes to be demolished. And those are the decisions that you're going to make. Okay, so the objective function, we want to maximize our total tax collection from our 4 types of homes. So depending on the type of home, this is the amount that you're going to be collecting. So for single homes, only 1,000. When you go to a bigger house, you will collect more taxes. Just take a look at there's no X5 in the actual objective function because you are not collecting any taxes. Okay, so the first constraint of the problem deals with the land availability. So you have a amount that you need to use for each type of home, and you have some availability in terms of the land that you have available. So you have the constraint for the land that you're going to be needing for each type of home, which is listed here. So to determine the available acreage, each demolished home occupies 0.25 acre lot. So that's a 0.25 H5 acres for the availability in terms of the space that you're going to have per home that you demolish. But also you need to consider that 50% is used for open spaces. So you have to take that into account. So the way that you do that is by knowing that only 85% of that space is the one that you're going to have available to build the home. Because the other 15% is for space and street and so on. So you can multiply that amount times the space available, and you will get 0.2125. So the resulting constraint is the space that you will need to build a home for each type of home, less than or equal to the space that you're going to have available based on how many houses you're going to launch. Okay? So using this, you can state your first constraint. Then you know that you can only demolish a maximum of 300 houses. So this is an easy constraint. And the constraints limiting the number of units of each type of home. So you also have that constraint. So you know 20% of the units should be single units, 10% double units, and 25% for the other two. So using that information, you can state these 3 constraints. That essentially tells you that for type 1 home, you only your houses needs to be for 20% of the total. Okay? And same for X2 and X3 and X4. So the last constraint is the budget that you have available. So construction and demolition costs should be less than or equal to the available budget, which is $50,000. So using the cost of building each type of home and the cost of demolishing a home, you can state this constraint for not going over the budget that you have available. And this is how the formulation will look like. Again, you have your constraints, you're trying to maximize your tax collection, and you have your bounds. Any questions? Okay, so again, I'm going to post a homework today. That homework probably is going to be due by Tuesday, depending on how long the homework is. You will see that I would list, let's say, a lot of problems, but you don't have to submit all of them. I just want you to practice. So you will only submit those that are listed to be submitted, but the other one is for you to practice for the exam. After Tuesday, I'm going to post the solution for all the problems, including the ones that you don't have to submit. So you can practice and have the solution when you're studying for the exam. Any questions? Okay, so I'll see you on Tuesday. Have a good weekend.